Yeah, good morning. The topic of today is CTL model checking with fairness. And what we are going to see is that model checking CTL with fairness for that we need a special procedure. First of all, what we have already encountered is that strong fairness conditions cannot be expressed in CTL. So we have first to find a way around this. Then once we are able to define these kind of strong, weak and unconditional fairness, the question is how to do CTL model checking in the presence of those fairness assumptions. And what we're going to do is that model checking CTL can be reduced, as we're going to see, to basically two procedures. Standard CTL model checking for most of the operators. For instance, existential next and existential until. And what we are going to need is we going to need a special procedure. So a special procedure to deal with formulas of the form existential box, and actually existentially box true or A actually is enough, as we're going to see. And these are the two ways that we're going to deal with. So we're going to need those two procedures. So first I'm going to explain how to express fairness assumptions in CTL. That means that we're going to adapt the semantics of CTL a bit. Then we're going to see that for next and for until, we can do a small trick such that we can reduce the model checking under fairness of those operators to standard CTL. And what we need is for existential box, we need a special procedure to deal with fairness. And this procedure is basically strongly based on computing strongly connected components, as we're going to see. Good. So that will be the, let's say, the roadmap. What about the complexity of this procedure? Well, what do we know if we do LTL model checking with fairness? So if we go back to LTL plus fairness, what we were doing basically is saying, okay, a state satisfies under a fairness assumption an LTL formula phi, if and only if S satisfies fair implies phi. And this was just an LTL model check, LTL formula. And therefore in the case of LTL, whether it is a strong fairness, weak fairness or unconditional fairness, we can always use a standard LTL model checking procedure to handle with this at the expense of expanding the formula a bit. So that means in terms of complexity, that the complexity of ordinary model checking of LTL is linear in the size of the transition system and exponential in the size of the formula. If we now add fairness, then actually in terms of LTL, this formula gets a bit longer, namely the length of this fairness assumption is going to be added. And that forms to the fact that now we are exponential the size of the original LTL formula plus the encoding of the fairness assumption. Yeah. Good. For CTL model checking, we have seen an algorithm which is can be dealt with in polynomial time. And what we see today with respect to the fairness assumptions, we're going to see that that we get a multiplicative factor in the complexity with respect to the number, the size of the fairness assumptions. Okay, so that's on one slide, complexity-wise, the difference between dealing with fairness in LTL and dealing with fairness in CTL. The price that we have to pay is that we need a special procedure. We cannot just use off-the-shelf CTL model checking. Well, as we're going to see, most of the time we can do it, but not always. So what were fairness assumptions? Just a short recap. We had three types of fairness assumptions. Ones in which we said something should happen infinitely often. We call this unconditional. Strong, if infinitely often something is enabled, we should take something infinitely often. And weak fairness, if from some point on always something is enabled, then you should take it infinitely often. Good. What was the point? Those formulas psi and phi, they were just propositional formulas. They were just basically atomic propositions or conjunctions of atomic propositions. Good. And then we reduced this to fairness, as I just explained. We were saying that a transition system satisfies an LTL formula under the fairness assumption if and only if every part, every fair part in this transition system satisfies this LTL formula, and that was just encoded by saying that if the part is fair, then it also should fulfill phi. If it's not fair, we don't care, because that was the reason of having fairness assumptions. Remember, ruling out those things that were not fair. Good. So for instance, if you have something like unconditional fairness, infinitely often A, this means that you take the negation of this and you take OR with phi, because that's exactly encoding this implication. So for CTL fairness assumption, we're going to make the following encoding. So we're going to encode fairness assumptions in terms of LTL formulas. So that's already the first somewhat, deviating step of what we have seen so far. So we're dealing with CTL model checking, but we're going to use LTL to code up. Actually, we're going to use a mixture of LTL and CTL to code up the fairness assumption. So what we have in that phi and psi are state formulas in CTL. So they can be arbitrarily nested state formulas. Yeah. So they could include existential and universal part quantifications. And then we say, okay, infinitely often we should visit a state satisfying this CTL state formula. Strong fairness says if we infinitely often visit a state satisfying the state formula psi, we should also infinitely often visit a state satisfying the state formula phi. And weak fairness, if from some point on we only visit states satisfying the state formula psi, then we should infinitely often also visit states satisfying the state formula phi. Good. So fairness assumptions are not CTL formulas. They're just a syntactic formalism to specify fairness assumptions. Yeah? Good. So for instance, in strong fairness, which has simply the form that we have a conjunction of several of those strong fairness assumptions, infinitely often psi j, then you infinitely often have phi j. The important point is that those psi's and phi's are state formulas in CTL. That means that now we have to define actually a new satisfaction relation, because we have a CTL formula that we want to check. We have a state, and we have those fairness assumptions, like a mixture of coding it up in LTL and CTL state formulas. So by induction of the structure of the state formulas, we're going to define this satisfaction relation models fair. This has no influence on the propositional logical formulas. Why not? Yeah, fairness assumptions typically only are important for infinite parts, and that means that for other kind of formulas of this form, they're not important. So there, this is just standard. So let's look at existential phi. It's what you, I think, would expect. So a state S satisfies under the fairness assumption fair, existentially phi, if and only if there exists a fair part. So if there exists a part pi starting in S, which is fair, and which satisfies under the fairness assumption phi. So we have to keep this fairness assumption there, because this phi can itself again have nested state formulas or part formulas that need to be influenced by this fairness assumption. Similarly, for universal quantified formulas, that means, of course, for all parts starting in S, if the part is fair, it should also satisfy phi. Good. Then what does it mean for a part to satisfy fair? Right? This fairness assumption is an LTL formula. Remember? An LTL formula where the state formulas are the CTL, the predicates or the propositional parts are basically the CTL state formulas. So how is this satisfaction relation defined? Well, this is simply that, for instance, if this is a formula of the form infinitely often state formula phi, then it means that this part pi, encoded as S0, as etc., S1, S2, satisfies this formula if and only if there are infinitely many positions along this sequence such that those states satisfy the state formula phi. Yeah? So this is the satisfaction relation with respect to fairness. This is the satisfaction relation, the ordinary CTL satisfaction relation without fairness. Yeah? So for checking the fairness assumption, we do not use the fairness here. We just use standard CTL semantics. Then we say a path satisfies this fairness assumption, well, in, let's say, the LTL way, infinitely often phi, infinitely often you have to visit a state satisfying phi. And that's basically it. Okay, so let's look at a small example. This is an example we have seen plenty of times before. Just let's look at the CTL formula. The CTL formula says infinitely often start. Good. Let's assume the fairness, the transition system doesn't satisfy this formula. Why not? Because, for instance, you can get stuck in this loop. But now if you take an unconditional fairness assumption, so a simple unconditional fairness assumption would mean you need to visit infinitely often delivered. Yeah. Now, if I impose this condition, then this counterexample that I just had by taking this loop infinitely often is not fair anymore. So this is ruled out by the fairness assumption, and that means that the transition system under this fairness assumption satisfies infinitely often start. Good, that's pretty simple because delivered is just an atomic proposition. You can also make things like this, infinitely often try to send, infinitely often delivered. You see that this is just, remember, an LTL formula. This means that if you have infinitely often in this state, you also need to be infinitely often in that state. That, of course, also rules out the same counterexample, namely this infinite path staying in this loop is no longer fair. That means the transition system satisfies the formula. Good, but now you can make things more complicated. So you can say something like the unconditional fairness assumption is infinitely often something. And this something is a CTL state formula. Okay? So this state formula says there exists a path such that next start holds. Okay, so how are we going to deal with these kind of fairness assumptions? Well, we first look at which states satisfy this state predicate existential next start. So you start by determining which state satisfying that there exists a next state which is start. Well, this is start. There is only one incoming arrow coming from another state, namely from delivered. So the satisfaction set is delivered. So this can be reduced in the same way as for CTL by saying this is the same as infinitely often delivered. And that was exactly the strong fairness assumption or the unconditional fairness assumption we had before. And that rules out this counterexample, and therefore under this condition, under this fairness assumption, the transition system satisfies the formula. Good. Now you can have things like this, a weak fairness assumption. If from some point on always you are in a state satisfying this state formula, there exists a transition to a delivered state, then infinitely often you should visit delivered. Good. How are we going to deal with these kind of fairness assumptions? Like with CTL, you start inside out. So the first thing we do is we try to determine the set of states satisfying this state formula. For that we use standard CTL semantics. Yeah? No fairness assumption. Yeah? So that's simply there exists next delivered. Now, which states have an outgoing arrow to deliver? That's only for try to send. So that's the singleton set try to send. So we can simplify this to this formula. And that means that from some point on, if you're always in try to send, then infinitely often delivered. Yeah. Now, does it rule out this part? No, because it does not satisfy this premise. Yeah. Because every time you're in the lost state, you're not in this try to send state. So therefore, you violate this formula. So it means that the transition system under this condition, well, that was the translation of this condition, does not satisfy infinitely often start. Good. So what is important? You have a fairness assumption. It can have arbitrary CTL state formulas as subformulas. You evaluate them according to standard CTL semantics. And then you're going to check whether under the fairness assumption the original CTL formula holds or not. Good. Similarly for strong fairness, same as before, this is the same state. So now you get infinitely often try to send, infinitely often delivered. That rules out, of course, the loop that goes via lost. So now you satisfy the formula. Good. Is this principle clear? Yeah? Good. Okay. So this is hopefully not a surprise that if S satisfies the CTL formula without any fairness assumption, that all paths eventually reach an A state, where A is just a plain atomic proposition, then under any fairness assumption, this is also true. Now, intuitively, this hopefully is clear because a fairness assumption rules out certain paths. If you know that a certain property holds for all paths, it also holds for a subset. That's the idea. Correct. But be careful. It is important that A is an atomic proposition. If A is an arbitrary CTL formula, which we allowed, then this is no longer the case. This is hopefully, this is true, this is easy. So does the same condition hold if A is replaced by an arbitrary state formula? And this is not the case, because you can have nested path modalities. It can be the case that for all box, here can be an arbitrary formula. For instance, there exists a path, blah, blah, blah. Now, if the fairness assumption rules out this path that satisfies exists, blah, 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 then this is no longer the case. Good. So for instance here, so for all eventually, the same as before, but now the subformula is this existentially box A. Yeah. Is this implying that S under any fairness assumption satisfies the same formula? Now, intuitively you are maybe tempted to say this is the case because this means for all paths and therefore definitely also for all fair paths, but you have to be careful because of this nested existentially quantified formula. So here is a counterexample. This free state transition system, if we check which states satisfy there exists a path which is completely red, then this holds for S1 and S0 and S1. So for which states satisfy for all paths, eventually you get into S0 or S1, right? Now this holds for S0 and S1 itself. Yeah? Because no matter where you start here, you immediately go to, you are already in S0, and for that state, the property also true. So now let's look at this fairness thing. So let's impose a fairness assumption. The fairness assumption says infinitely often B. Then the satisfaction set under this fairness assumption, does there exist a path which is completely red under the fairness assumption that you should infinitely often visit B, is of course empty. Yeah? Because you have to visit this state infinitely often, but that you cannot do by having a path which is completely red. So here the satisfaction set is empty, and that means that the satisfaction set for this formula under the fairness assumption is empty. Yeah? And you see that this set differs from that set, and therefore this statement is not true. So it's the nesting of the formulas which basically complicates life here a bit. Good. What is going to be important is the subformula their existential box true. So similar example as before, only the colors I think have changed. So if you have the fairness assumption infinitely often red, right? Which states satisfy the formula there exist box true? Now true holds for every state, right? So existential box true simply means does there exist a path? Yeah. This fair says does there exist a fair path? So for which states does there exist a fair path? Well, for this one definitely does, because there exists a path that moves here which satisfies infinitely often red. So this path satisfies the formula. Also this state satisfies the formula because S2 of course can only do one thing, namely taking the self cycle infinitely often. So those two states satisfy this formula, and that's the conclusion. Set fair of existential box true is the set of states that have at least one fair path. And that also means that a fairness assumption is realizable. Remember what was a fairness assumption being realizable? It means that every reachable state has at least one fair path. And that means that the set of reachable states must be a subset of the set of states that have at least one fair path. Good. So now we get to the model checking problem for fair CTL. We have a finite transition system, a CTL formula, and such a fairness assumption fair. This LTL formula where the subformulas are CTL state formulas. Question, can we algorithmically decide whether my transition system satisfies the CTL formula under the fairness assumption fair? Good. For instance, we can have a strong fairness assumption like this. We have a conjunction over k subformulas, so k strong fairness assumptions, saying infinitely often psi I1 implies infinitely often psi I2. So what we're going to assume in this algorithm is first, like we did for the CTL model checking algorithm, I'm assuming that the CTL formula phi, so this formula that we need to check, is in an existential normal form. So the only modalities that we're going to deal with is existential next, existential until, and existential box. That's exactly what I wrote down here. We have existential next, existential until, and existential box. Good. So first, what we do is we do a pre-processing. That's exactly what I did in the example. We take the fairness assumption, right? This fairness assumption may have arbitrary CTL subformulas. So we may have something like infinitely often there exists a path such that blah 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 holds, implies infinitely often existential A until B. No? This is a CTL state formula, this is a CTL state formula. The first thing that we do is we apply a standard CTL model checker to check which states satisfy these two formulas. Okay? So we compute the first step, compute SAT of this subformula plus the satisfaction set of that subformula. Good. Now what we do is we introduce two new atomic propositions. So what I'm going to do is I'm going to simplify this formula. So I'm going to say infinitely often, yeah, I don't know, A1, this belongs to this formula, implies infinitely often an atomic proposition for this formula. Yeah, so I'm syntactically going to replace these CTL state formulas, this one and that one, we're going to replace by atomic propositions. Yeah. Then it's obvious, I hope, that we're going to adapt the labeling. All the states satisfying this thing are going to be labeled with this state form for this atomic proposition. So we have that this atomic proposition is going to be labeled in a state if and only if S belongs to the satisfaction set of that formula. Similarly, we have that atomic proposition is going to belong to a state if and only if that state belongs to the set of states satisfying that formula. Good. What did we do so far? We basically now reduce this to a standard, if you want, an LTL fairness assumption. This is in effect an LTL fairness assumption. Yeah, and that's what we're going to use then for the rest of the model checking algorithm. Good. So that's what I call pre-processing. Good. So that's what I just explained. So you compute for all these subformulas the satisfaction sets with a standard CTL model checker, and you replace them by fresh atomic propositions. Good. So that means that in the end we have reduced our strong fairness assumption to a shape of the following form. still we have K strong fairness assumption and infinitely often some atomic proposition Bi, infinitely often some atomic proposition Ci. Good, that was the pre-processing. Now we build the pass tree of phi, so now we take the CTL formula that we need to check. So we take this formula and do this in the same way as CTL. For all the propositional logical formulas, this is standard CTL. We don't have to adapt anything. This, what we're going to do is we're going to reduce this to standard CTL, which I'm going to explain in a minute. And for that, we need a special procedure, namely via analysis of strongly connected components. Good. So the propositional logical fragment is exactly as for CTL. Whether you have a true or an atomic proposition or a negation or a conjunction, the way to compute this satisfaction set is exactly the same as we have seen before. That's easy. So now we go to existential next and existential until. Good. So the treatment of existential next. So let's first look at an example. So this transition system, and suppose that this is the fairness assumption, says infinitely often we have to visit the red state. Then, does there exist a path such that next, so that the state satisfies it has a successor which is green, is not applied to S, right? Because this state is not fair. Yeah, this state will never visit the red state and definitely not infinitely often the red state. And that's the problem. The problem is that this state does not have any fair computation starting in that state. And that's what we're going to use. So we're going to introduce an additional atomic proposition, A fair, for all the states. And we're going to say that this special atomic proposition, the state will be labeled with this special atomic proposition if and only if in that state at least one fair computation will start. Good. And that means that in our example, these two states are fair because starting from this state, there is at least one fair path, namely the one going to the right. And from that state, this state is fair because the only path starting here is fair. That means we're going to label these two states with this new atomic proposition, which is indicated by this brown circle in that state. And that means that in the end, what we need to check is, in order to check whether their existential next green, we're going to check, does there exist a path such that next green and this new atomic proposition holds. So for all B, we're going to check if we have a formula existential next atomic proposition, and we have to check this under a fairness assumption fair. This is to be true if and only if S satisfies the formula there exists a path so that next B holds and A fair. Good. We're going to shortly show that this is the case, and this works as follows. Now maybe I make some space. Yeah, I have an empty. So the lemma says the following. I have a state S under fairness assumption existential next B, A, if and only if there exists a direct successor of S such that S prime satisfies A and S prime has at least one fair path. So S prime satisfies existential box true under the fairness assumption. And this is nothing else than saying that the fair paths, the set of paths that are fair starting in S prime is non-empty. Good. Assume that S satisfies under the fairness assumption next A. Yeah. And this holds for all fairness assumptions, right? I mean, I did not make any assumption about the shape of my fairness assumption. So assume that this holds. Then there is a fair part pi starting in that state, so S0, S1, S2, starting in S, so that means that this equals S, with S1 being an A state. Since pi is fair, the part starting from 1, which is the part S1, S2, S3, so the suffix of pi, is also fair. Thus, S1 is a successor of S. It satisfies A, and S1 satisfies, under the fairness assumption, existential box. True, because it has at least one fair part, namely this part, pi, you take the suffix of it. The other way around. Assume S prime is a successor of S. S prime satisfies A. And S prime satisfies this formula. Because of this, it means there exists a fair part pi prime that starts in S prime. But then, if I take this part, so I take the part S prime, S1 prime, S2 prime, S3 prime, etc. And now I extend it with S. Yeah, so now I add S in front. Then this is a fair part in parts of S, such that since S prime satisfies A, this part such that it satisfies next A. Thus, S satisfies there exists a part next A, and it also has at least one fair computation that satisfies this. Yeah, so in this direction, I use the fact that if a part is fair, any suffix of it is also fair. And the proof of the other way around, I use the fact that if I have a fair part, a blue one, I can prefix it with every, basically, finite prefix, and I also get a fair part. Yeah? That's basically everything what happens in this proof. Why is this property of interest? Now, this property is of interest because now if I need to check this formula under a fairness assumption, it allows me to just check the right-hand side. And that means basically we need to check, this is the same as saying that S satisfies under standard CTL model checking, there exists a next A. This S prime is a successor. So that's just a standard CTL model checking, standard CTL. And we need to check this. Now, why is this good? Now, this is a special instance. Yeah, existential box true is a special instance of existential box A. If I just assume every state is labeled with A, then this is exactly the same. So this special procedure that we're going to need later on anyway can be used here for this. And that's what we're going to exploit. Good. So what did we just saw? We want to check whether state S satisfies under this fairness assumption there exists a path next B. The way we're going to do that is, thanks to this lemma, it says if and only if S satisfies under the CTL semantics, right, no subscript fair here, that there exists a path such that next B holds, and this atomic proposition. And this atomic proposition is exactly identifying all the states satisfying this formula existential box true under the fairness assumption. And intuitively speaking, this simply says there is a fair path starting from here, period. Good. And the same, and the proof goes completely analogous, you can do it until. So if you want to check whether for state S under a fairness assumption the state satisfies does there exist a path for which C holds until you reach a B state, this is equivalent to saying under the standard CTL semantics S satisfies there exists a path such that C holds until you reach a state where B holds and that state is fair. That means from that B state there is at least one fair path starting from there, and that is indicated by this extra atomic proposition. Okay. So this means that for model checking those two formulas, you can just take your off-the-shelf CTL model checker. But you need one extra bit, namely you need to check which states need to be labeled with these atomic propositions, or equivalently, which states satisfy under the fairness assumption this formula. Good. Any questions? No questions. Good. Okay, so here is a short, small example. So this is my transition system. This is the formula I want to check. Does there exist a path that eventually reaches a C state? Good. But I'm going to impose a fairness assumption, and the fairness assumption says if you infinitely often visit a light blue state, you should infinitely often visit a dark blue state. Good. So one thing you see is that this state is not fair. Why not? There is no fair computation starting here because there is only one thing, namely the self loop, which means you infinitely often visit a B state, but you do not infinitely often visit a C state. So this state is not fair. The other states are fair. In particular, also this state is fair, yeah, because it never visits a B state. Yeah, from here, there is no computation that ever will reach a B state, so this premise is vacuously true. So these four states, indicated with this brown circle, satisfy that they are fair, which means rather than checking this formula, existential eventually C, we're now going to check eventually there exists a path eventually C and fair. So the question is, does there exist a path starting from those four states that eventually reaches a C state and that is also fair? So that's in particular that state, and that's clear to see from the initial state you can reach this state, and therefore the original property under the fairness assumption holds. So therefore the transition system satisfies this formula, and that means by the construction we just have seen that the transition system under the fairness assumption satisfies this CTL formula. Good. Same for until. Small example. Suppose this is my formula. Does there exist a path that reaches a C state via non-B states? Good. We're going to impose a fairness assumption. Let's assume this is a strong fairness assumption, the same as before. Infinitely often light blue means infinitely often C. Which states are fair? That's the first thing we're going to check. Well, this state is not fair because the only way it can do it can move here. That means infinitely often light blue, but not infinitely often dark blue. Also that state, of course, for the same reason as before, is not fair. This state is fair. Why is this fair? Thanks to the self-loop. There exists a path which is fair because this never visited a B state, and therefore the premise is vacuously true. So the only state which is equipped with this new atomic proposition is the initial state. Okay? Good. So it means that the set of states satisfying C, I mean why C, because we're interested in this formula, and A fair is empty. This C state is not equipped with this new atomic proposition, and that means that the initial state S does not satisfy that there exists a path that reaches this state that doesn't exist. Yeah. That cannot be the case, but that means that it does not satisfy under the fairness assumption this CTL formula. So the final answer to this question is false. Good. Question?
Isn't it that the yellow state fulfills that not be holds while C is reachable in a fair way?
No, but you cannot reach C. You cannot reach a state. The point is there is no C state which is also fair.
Oh, okay,
Yeah? There is a C state, but the bad point about this example is from there is no fair computation starting, and therefore this is not a state which is a good state to reach. Yeah? Other questions? No? Good. Okay. So now you could think, well, why don't we do the same trick, right? I mean, what we just have seen is that basically we have seen that if I want to check this under a fairness assumption, existential next A, we transform this to S satisfies under the standard CTL semantics, existential box next A, and this A fair thing. Yeah? And this was existential true under the fairness assumption. The same works for until. This is reduced to S existential B until C and A fair. Yeah. So now the question is, can we not do the same for box? Yeah, so would it be possible, that would be cool, if we can do something like this and then reduce it to existential box A and A fair, because that would mean that we can use again a standard CTL model checking procedure, but that doesn't work, as this counterexample is going to show. So that's the special thing we need to treat. So this is wrong. Counterexample. Suppose the fairness assumption says infinitely often we have to visit the red state. Then which states are fair? Now this state obviously is fair because of the self loop. This state is fair because it can move to that state after taking this self loop 0 or more times, and then this also is a fair computation. Yeah. Good. So take this state as 0 and now look at particularly the behavior that you stay in that state. So that state S satisfies there exists a path which is always satisfying C and A fair, because for instance you can stay here. This state is A fair, right, and it satisfies C. So definitely this is a statement which is true, because we can take the self loop. That's what is stated here. But of course it's not fair, right? Because this computation does not satisfy infinitely often red, which is the fairness assumption. Yeah. So therefore this state does not satisfy under the fairness assumption. There exists a path which is always C. Yeah, because there is this path which is always C, but that path itself is not fair. Yeah. So this procedure, this step, does not work. Good. So what are we going to do? Therefore, we need a special operation for existentially box formulas. And please remind that this formula, existential box true, is just a special instance from existential box A. Yeah, so if we can solve this, we also have immediately a procedure to solve this. So far what I'm saying, CTL model checking with fairness is CTL model checking with just one single twist. The twist is existential box, in a sense, apart from the preprocessing. Good. So let me explain this principle. Suppose I have a formula of the form existentially box with an arbitrary CTL state formula. So psi is some kind of nested CTL state formula. And this is my transition system. I have some fairness assumption. The fairness assumption is here, in this case, a strong fairness assumption. And I'm interested in checking whether my transition system satisfies under this fairness assumption. Does there exist a path which is completely only visiting states satisfying the CTL state formula psi? Good. The thing we're going to do is we first, because we do this bottom-up computation over the path tree, we can assume, without loss of generalization of generality, that we have already calculated the set of states under the fairness assumption satisfying psi. Okay, so for this we use the CTL, the fair CTL model checker. Good. So I know which states satisfy this formula under the fairness assumptions and which one do not. So I'm going to replace, like we did for CTL model checking, this formula with a fresh atomic proposition, A psi. Let's suppose that those 4 states satisfy psi. So what happens is that I'm going to label these states with this fresh atomic proposition A. Good. What can I now do? As we all hopefully know, now I can reduce this formula existential box psi to existentially box A. Yeah? So that is the reason why it suffices to only consider the case existential box atomic proposition. Yeah, because if there would be an arbitrary state formula by the bottom-up computation over the path tree, I can always replace this by an atomic proposition. Good. Now we have to calculate sat-fair existential box A. Good. How are we going to do this? We're going to cut out, basically remove all the states that do not satisfy this new atomic proposition. This is in particular this state in this example, yeah, because it's not satisfying the formula psi. So definitely from those states there will not be a path satisfying box psi. So rule it out. So we look at this subgraph, and now what we do is we look at the fairness assumption. The fairness assumption says the following. If you infinitely often visit a light blue state, you infinitely often have to visit a dark blue state. Okay? Good. Which states here are fair? Well, does this state have a fair computation? No. Yeah, because it infinitely often visits a light blue state but never a dark blue state. Does this one has a fair computation? No. This one? No. That one? No. Yeah, because there is only one possibility, namely to go to the sink, which is not fair. Good, so this digraph does not contain any fair path. And that means that this transition system under any fairness assumption does not satisfy this formula because it does not have any fair path. Good. The important point about this slide is if we start with some arbitrary formula, existential box CTL state formula, in the end everything is reduced to existential box atomic proposition. And that's what we need to deal with. Good. So how to deal with existential box atomic proposition? That's the case. Yeah. Good. So the goal is to compute this set of states satisfying existential box A under the fairness assumption. Good. If all states are labeled by A, then this technique is indeed exactly a procedure to compute this set existential box true, which is exactly what we needed for next and for until, because there we have this existential box true. So this is a special instance. So I'm going to explain this for strong fairness. The explanations for weak fairness are actually quite, well, it's an adaptation of it, but relatively a straightforward generalization. Good, so assume that the fairness assumption is a conjunction of k strong fairness formulas, infinitely often bi, infinitely often ci. So S satisfies under this fairness assumption there exists a path which is always A, if and only if there exists a path fragment starting in S, so S0 equals S, and at some point you get to a cycle. Yeah, we need to have an infinite path, finitely many states, so we need to end up at some point in a cycle. What do we need to know? Well, this cycle needs to have at least one edge, so that means between n and n plus r, this r is at least 1. We start in the state S, and it's a cycle. That means this state is equal to that state. What else do we need? We need that this path needs to be completely satisfying A. So obviously any state on this path needs to satisfy A. And now the fairness assumptions. This path needs to be fair. So that means that if I take the prefix to the start of the cycle and then take the cycle infinitely often, that this needs to be a fair computation. What does that mean? Now we have to fulfill all these conjunctions. So that means that in particular for all I, the following should hold. Either along the cycle there is no bi state, or along the cycle there is at least one ci state. So the way to see that is the following. We start in S, then there is some path that leads you to some state, what is it, Sn plus 1. And now you end up in a cycle. So you get back there. And now you have to fulfill the fairness assumption. The fairness assumption says, okay, infinitely often bi implies infinitely often ci. So that means that if on this cycle there is no bi state, there is no bi state, then it immediately means that you fulfill this condition that infinitely often bi implies infinitely often ci. Because this premise is not fulfilled. Good, that's option 1. The other option is you need to have at least a ci state there. So you need to have at least a ci state somewhere here. So here is a ci state. And if there is a ci state, then you automatically fulfill the fairness assumption I, because you visit this ci state infinitely often along the cycle. No matter whether you visit a b state infinitely often, but that doesn't matter anymore. Good. So what does it mean? Consider this example. There exists box A. The dark states satisfy A, the other ones do not. So the first thing we do is we analyze the subgraph that only contains states satisfying A. So we're going to remove all the light colored states. This gives us this subgraph. Okay? Now what we need to check, this is the subgraph for which basically potentially all the states can satisfy there exists box A. Can, doesn't have to be. Now suppose that I have as fairness assumption the following fairness assumption. So this is the case for k equals 2. Infinitely often orange means infinitely often red, and infinitely often light blue implies infinitely often dark blue. That's the fairness assumption. So this was the original transition system. This was the digraph that I obtained by only looking at the A states. Okay? So the coloring corresponds to the atomic propositions in this fairness assumption. So now what we need to do is we need to check whether, for instance, S0, the initial state, is fair. So what does it mean? For instance, you can go from S0 to S1 to S2 and then cycle around between those two states. Question, is this fair? Now we have to fulfill both conditions. So let's first look at the first condition. This cycle does not contain, it contains a red state, so you infinitely often visit C1, so the first condition is fulfilled, regardless of whether we visit any orange state or not, it's fulfilled. Now we have to fulfill the second condition. The second condition says, okay, I have to infinitely often dark blue, which is infinitely often dark blue. So therefore, this also satisfies this second fairness assumption. So this is a computation which is fair. Therefore, in this subgraph, this was the subgraph that only contains the A states. Therefore, the transition system satisfies under the fairness assumption this CTL formula, because in this subgraph there is a fair path, the one that I just indicated, and that satisfies by construction existential box A. Good. So here again is the condition that we have seen before. So what we are looking for is actually, we look for cycles, and those cycles need to fulfill either they don't have any, they have at least one CI state, or they have no BI state. Yeah. Good. What we do is we do this in the digraph GA because we're interested in existential box A. So we don't check this in the original transition system. We look at this digraph because that one only contains the A states. This is a cycle, so it's a strongly connected thing, but it doesn't mean that it's a strongly connected component because it does not need to be maximal. Yeah, I mean, I think that even occurs in the previous example, right? This is a maximal strongly connected component, yeah, but my argument was not about this maximal strongly component, it was about the cycle that only contains S1 and S2. Yeah? Good. So the way to phrase it in a different way is that we want to check existential box A under this strong fairness assumption. That holds if and only if there exists a non-trivial strongly connected node set. What's a non-trivial? Non-trivial means that it has at least to have one edge. So this thing is trivial, yeah, and this is non-trivial. Or for instance, this between two states and you go back and forth. This is non-trivial, but this is trivial. Yeah? You need to have at least one edge. Strongly connected node set. Strongly connected simply means from every state you can reach every other state. On the graph GA. So you take the transition system, remove all the non-A states, and you work on that subgraph. Such that the following holds. That one needs to be reachable, and, well, on that in that connected node set, either there is no BI state or there is at least one CI state. Because we need to fulfill this condition, yeah. If there is no BI state, this condition definitely is fulfilled. And if there is at least one CI state in D, then that condition is also fulfilled because we cycle around in D infinitely often. Good. What is important, which I already actually stressed, is that the subgraph I'm looking at are strongly connected, non-trivial, but they don't need to be maximally strongly connected. In a sense, even it could be the case that there is no maximal strongly connected component satisfying 1 and 2, but it's enough to look at the subgraph of the strongly connected graphs. Good. Okay, example again. I want to compute SAT existential box A. First step, remove all the non-A states. This gives me this graph on the right. Okay, good. Now we need to look at the fairness assumption. So what is the fairness assumption? Assume that the fairness assumption has the following shape. Infinitely often orange implies infinitely often red. and infinitely often light blue implies infinitely often dark blue. Good. This was the subgraph that we are considering. Yeah. So what do we need to check? We need to check in this subgraph, does there exist a fair path in that subgraph starting in the initial state? So we want to check whether from the initial state there is a fair path satisfying existentially box A. So what we are looking for? We're looking for a strongly connected set of states. For instance, the one that are indicated S1 and S2. Claim the path starting from S0 and going among those two states is fair. This is, I hope, because it has at least one red state and it has at least one, on the cycle it has at least one dark blue state. So both fairness assumptions are satisfied by this cycle. The cycle is reachable from the initial state, and therefore it follows that actually the set of states satisfying existential box A fair is definitely S0. It also contains the two states on the cycle itself, and it contains S3 because this cycle is also reachable from S3.
Just a small question about the satisfaction or fairness of S1. I don't think that S1 is satisfying dark blue, but it's the purple color, so the cycle is satisfying not B2 and not.
Okay, you are more sharp in colors than I am. On my slide, yeah, it's hard to see even. This looks slightly different from the other. I agree. Yeah, even if I increase my resolution. Yeah. Okay, I see the point. This is blue, dark blue, and this is different from dark blue. Okay, a bit. Yeah. Okay, good. Okay, very good. Nonetheless, this cycle satisfies the fairness assumption, but not for the reason that I mentioned, namely infinitely often visits the blue state, because apparently it seems to be I'm colorblind. Because you never visit a light blue state, right? Good. Thanks. Good. So the conclusion is still correct, despite my color blindness. That this is a fair path because we reach this cycle which is fair. That means that the set of states satisfying existential box A fair, you look at this subgraph and you look at all the states that can reach this fair cycle. Right? This one can reach the fair cycle, of course the points themselves on the cycle, but also S3. This one does not satisfy because it cannot reach the cycle. Good. The treatment of existential box for CTL with fairness is now as follows, and we only do this for strong fairness. And I'm going to provide the details for basically three simpler cases. The first case says unconditional fairness. Then we're going to consider one fairness assumption, so on the conjunction only of basically over k equals 1. And then we're going to check arbitrarily many by first looking at the case for 2 and then the case for arbitrarily many. Good. Unconditional fairness. So existential box under unconditional fairness. Assume that the fairness assumption says infinitely often Ci, and I have a bunch of those conditions, so k of them. Then a state satisfies existential box A fair if and only if there exists a non-trivial strongly connected component in the subgraph GA, so I carved out all the non-A states, which is reachable, and that has at least one Ci state. Good. So fairness assumption infinitely often C1 and infinitely often C2. Is there some non-trivial component that I can reach here, which has a red state and a green state? Doesn't seem to be the case, right? So this does not satisfy this formula Yeah, because this is a strongly connected component, but it only contains a green state. This is a non-trivial strongly connected component, but it only contains a red state, but we don't have one that contains both. So those are the two strongly connected components. If you change the picture a bit, so this satisfies the formula because now there is a strongly connected component which contains both a green state and a red state. So that definitely is now satisfying and is reachable from S. So S satisfies, under the fairness assumption, there exists a part which is always satisfying A. Good, that was unconditional fairness. What about strong fairness? One condition. Infinitely often orange implies infinitely often red. So the way to do that is the following. Suppose this is already the digraph GA. So this is already the sub-transition system where I removed all the non-A states. Good. From this initial state, as there are two strongly connected components reachable, this one on the left, that one on the right. And what we need to check is, does there exist a fair path? That means, does there exist a strongly connected component that, for instance, has at least this red state? So for instance, this one. The way that we're going to do this is as follows. We're going to take a non-trivial strongly connected component, and we're first going to consider those that have at least a C state. That means that this state satisfies existential box fair because it can reach this strongly connected components. This one is fair, and therefore the state satisfies this subformula. Suppose that this is the subgraph. Same fairness assumption as before. Claim S satisfies fair existential box A. How are we going to check this? Because there is a strongly connected node set, namely these two, which does not contain a B state. So you should not make the following mistake, is that you say, well, this is a strongly connected component. Well, this is infinitely often orange. It does not have a red state, so this is not good. That is okay. But if you look here, there is a strongly connected component that contains an orange state. Right? It does not contain a red state. So you may argue this is bad. But this strongly connected component has a subgraph which is also strongly connected, namely this one, which does not contain an orange state. And that's okay, because that means it's fair. So don't look at the maximal strongly connected components, but you have to look at strongly connected components, not to the maximal strongly connected components. That is important. So here is a strongly connected node set, D. It's reachable from the initial state, and it's fair because it has no orange state. Good. So what is the observation? The observation is the outermost thing is a strongly connected component, that contains a strongly connected component of the graph if we remove the orange state from this graph. So we look at GA, the graph we had before, but if you remove all the B states, then this purple cycle, which was important to us because that was the argument for the transition system satisfying the formula, we can find this by looking for strongly connected component of a graph where we first remove the orange states. Good. So by two strong fairness assumptions like this, then we have a graph like, for instance, here, where we again removed all the non-A states. We have two strongly connected components. This one is the first one. It does not have, now I have to be very careful with the colors, but this is really, it has no dark blue state. I think we agree on this. It does not have any dark blue state, so definitely it fulfills the second constraint. what we're going to do is you analyze this component C1, but you're going to remove the light blue state. We're going to remove the light blue state for the analysis of the first constraint, which is this infinitely often orange implies infinitely often red. What is the point? The point is that this strongly connected component is bad. Why is it bad? Because it is infinitely often light blue, but it's not infinitely often dark blue. So it does not satisfy the second constraint. So what you can do is you can remove the light blue state here. This is no longer a cycle anymore, and therefore from there it's not fair. So the second SCC, what we can do is the following. It has no red state. Yeah? So it has no red state. And now the only thing what we need to do is to check the second condition. Because it has no red state, right? We can, this is vacuously fulfilled. So the idea is remove the orange state. That's what we're going to do now. Because we know already that we fulfill the first fairness assumption. Yeah? So there's no need to look at this orange state anymore. And that means if we want to check the second condition, we're going to remove this orange state first, and then we're going to look at the remaining subgraph, and now we're going to look for a strongly connected component in order to check whether the second condition is fulfilled. Good, and that's this subgraph, and that subgraph is okay because it has a dark blue state, this one, and you visit this infinitely often, and it's reachable from the initial state. So we can conclude this initial state satisfies this formula because there is a fair path in the reduced subgraph GA that only contains A states starting from the S thing.
But the argument is not that we already fulfilled the first fairness condition, is it? Because otherwise we could have just kept the whole component we had already found, and there would be no need to remove the B1 state because it would be okay for it to be there because we fulfill the condition, and there would also be another state, right? So what I'm saying is we're removing it because we do not fulfill the first fairness condition and are searching for a sub-component.
Exactly, okay, yeah. That's correct. So you remove the orange state because we do not fulfill the first fairness assumption. Yeah? And that's the same argument actually, sorry if I explained this, this is similar here, right? Where we remove the light blue states because we do not fulfill the second condition. Yeah, absolutely, you're absolutely right. But this principle of removing states, if you do not fulfill certain sub-constraints that you already have seen before, is used in the algorithm to check if you have, for instance, k conditions, here we only have 2, to reduce the whole thing. Good, so this is how it looks like. The first thing we do is we take the transition system and we only contain the states that have satisfy A. That's the first step. Then we consider all non-trivial strongly connected components of this graph GA. If this strongly connected component is fair, then I'm going to add this component C to the set of fair components. And after having constructed, doing this for all non-trivial SCCs, what I do is I compute the set of states of existential box A as being all the states that are, let's say, for which 1T is reachable. Yeah. So if you look at the set of reachable states starting from S, that has to be at least one state that is also in such a fair, strongly connected component. Good. The complexity of this is linear in the size of the transition system. And you have to consider all fairness assumptions, and therefore you get as multiplicative factor the number of fairness assumptions. Good, let's look at this check fair. So this is a recursive algorithm that looks as follows. I want to check C, What was C? If you go back, C is a strongly connected component. So I want to check whether a strongly connected component, you have the number of fairness constraints, and these are all the K fairness constraints. This gives true, that's the intuition, if there exists a cyclic path fragment in this component, or there is a subgraph in this strongly connected component, which is, of course, connected. So this is this path that satisfies all the strong fairness assumptions, and otherwise it gives you false. Good. Quite quickly, the code. The first thing you check is whether it's, I mean, if this is the condition, and now I have to be careful, this is orange and this is red, right? So the first thing you do is whether it contains a red state or not. So that happens in the first line. Now you choose one of the fairness assumptions, 1 out of K, that has no red state. Now you remove all the states that are orange. That was according to exactly the procedure we have seen before. If the resulting graph is acyclic, then it cannot be fair. And otherwise, for all non-trivial SCCs, you're going to check the remaining conditions. That means that you're going to contain, for this non-trivial SCC D, you're going to invoke recursively the procedure check fair on D with 1 constraint less. Good. And this has the complexity which is linear in the size of the strongly connected components times the number of components, because you do K times this recursive invocation. Good. So the procedure now looks as follows. Fair CTL. First, we calculate the set of states which are fair. That's exactly according to the algorithm we just have seen, with the twist that the atomic proposition now is simply true. We label all the states that are fair with this new atomic proposition fair. And now you do a recursive descent over the parse tree. So you consider all subformulas psi of the original formula. If the formula is of the shape, the subformula existential next atomic proposition, then what we just have seen, you invoke a standard CTL model checker, so you compute SAT, no subscript fair here, of the CTL formula existential next A and A fair. And that is the set of states satisfying this subformula under the fairness assumption. You do the same for until. So if you have A1 until A2, you invoke a standard CTL model checker with the CTL formula existential, there exists a path A1 until A2 and a fair state. And that is the result. For existential box, we just have seen the procedure, at least for the strong fairness case. So you can compute this SAT fair psi there. Then you replace the subformula with a fresh atomic proposition, and then you check if you have checked all the subformulas. At the end, you end up at the root of the tree, and you check whether all initial states satisfy this formula. And then you return yes, and otherwise, if there is an initial state not in that set, you return no. Example. Example with this small communication protocol that we have seen before. I'm interested in the CTL formula which is written down on the right, and assume that the fairness assumption says infinitely often I visit a state for which this CTL state formula holds, there exists a path that eventually leads to the del state. Good. The first thing that we're going to do is pre-processing. So the pre-processing says, look at the fairness assumption, try to check which states satisfy the fairness assumption. So we're going to check which states satisfy there exists eventually del, without taking the fairness assumption into account, just plain CTL. So you look at the transition system and you check which states satisfy there exists a path eventually goes to del. This holds for all states except for the error state, but for all other states you can eventually reach the delete state. So this means that I can now replace this fairness assumption by this fairness assumption infinitely often C. Good. Now I need to compute as a second step of my CTL procedure which states are fair. Yeah? So which states can infinitely often visit a C state. Yeah? Good. Every state satisfies C except the error state. Yeah? So these 4 states are fair. Yeah? This state cannot, of course, because it cannot visit infinitely often any other state. So these are the fair states, the yellow ones. So I label them with this atomic proposition A fair. The first thing I do is I replace this CTL formula and I transform it into existential normal form. That's here relatively easy because this just becomes a negated existential normal form and this disjunction becomes a conjunction. Now what we need to do is we need to check this formula. Okay? So the way to do that is this was the existential normal form formula. We work S for CTL inside out, the bottom up or recursive descent over the path tree. So which states satisfy not lost and not del? That's pretty easy. Those are the 3 states in the middle. So that means that I can replace this subformula by an atomic proposition. This is this purple A. Now I can look at the next subformula, existential next A. Which states satisfy, which states have a neighbor which is now colored purple. I think this is basically all the states. But now you have to do this for the fair paths, right? Because you have to compute sat fair existential next A. So what we are going to do is we reduce this to CTL model checking of existential next A and A fair. These 2 states are the only ones which are purple and which were yellow before. How can we see this? Here we see that these are the fair states, all states except the error state. These states satisfy the atomic propositions, so the only 2 states satisfying A and A fair are start and try. Yeah. Good, and that means that, so that was back. Yeah. This part is satisfied by the 2 yellow parts. Which states satisfy now? There exists a neighbor which is yellow. This holds, for instance, for lost. It holds for start. It also holds for del. Yeah, so for those 3 states, the formula holds. Yeah, because from those green states, I can reach one of those 2 states. Good. So that means that I can replace this formula by means of some subformula. So now I have to take the negation. Well, that's easy because now I take the negation of those 3 states, which are the 2 remaining states, which are try and error. That's the complement of the set I just computed. Now I replace them by an atomic proposition, for instance B. So try and error are the only states labeled with B. Now I have to invoke existentially eventually B. How does that work? That's existentially eventually B. That was equivalent to the CTL formula existentially eventually B and fair. Remember, everything was fair except the error state. These were B and A fair. That's only the try state because the error state is not fair. So the question is, does there exist a path eventually leading to the try state? And that's true for those 4 states over here. Yeah. This includes the initial state, and therefore, after all this work, the transition system satisfies this formula. Yeah. Good. Are there any questions on this example? No? Good. Okay, I skip this example. I'm going over this very rapidly. You may ask yourself, why do you use CTL with existential normal form? What happens if you have universal form? then this trick does not work anymore. You have to be a small twist to it. So for instance, for all next A, you cannot replace by for all next A and A fair. I'm going to skip the example also because of time issues. But the point is that you can do the following. You have that S satisfies under a fairness assumption for all next A, if and only if S satisfies for all next, if A fair holds, then A. So again, you can here use a standard CTL model checker, but you have to use this subformula and not this subformula here. The same holds for all box and so on. Also, that doesn't work. Good, let's summarize. So what we have seen is that the CTL fairness assumptions are a somewhat mixture of LTL, like infinitely often, or persistence kind of properties that you cannot express in CTL. Then we have defined a CTL satisfaction relation that takes these fairness assumptions into account. And this you should just see as a syntax to write down fairness assumptions. Then the semantics is important because that takes those fairness relations into account. And then the model checking thing is we have seen that existential next, existential until. I did not treat this, but for similar reasons for all next and for all box, you can reduce to standard CTL model checking. For existential box, and similarly for the dual for all until, you have to analyze these strongly connected components or subset thereof, but that's what you can do by removing states. Everything can be reduced to analyzing strongly connected components. Complexity, this was the complexity of CTL model checking. The extra cost that we have to take into account for dealing with the fairness assumptions is this multiplicative factor, the size of the fairness assumption. Good. That's it for today. Friday, I'm going to deal with CTL star, where we are seeing combinations of CTL model checking and LTL model checking.